Loops don't just repeat actions, they build up results. A 3-line for loop can sum every integer from 0 through 9. The same pattern handles factorials. But one subtle mistake trips up nearly every beginner. The off-by-1 error in Python's range function. Let's master the accumulator pattern and learn to squash that bug. The loop body can manipulate the loop variable to build useful results. The most common pattern is accumulation, keeping a running total. Here's how it works for summing the integers 0 through 9. We start by setting my sum to 0. This variable is the accumulator. Next, the for loop, for I in range of 10. Inside the loop body, my sum increases by I. After the loop finishes, we print my sum. Range of 10 generates values 0 through 9, 10 values total. Each pass adds the current value of I into the accumulator. The final printed result is 45. Let's trace through memory step by step. Before the loop, my sum is 0. First iteration, I equals 0. My sum equals 0 plus 0, still 0. I equals 1. My sum equals 0 plus 1, giving 1. I equals 2. My sum equals 1 plus 2, giving 3. I equals 3. My sum equals 3 plus 3, giving 6. The pattern is clear. Each iteration, the current value of I gets added to whatever my sum already holds. Continuing, I equals 4, my sum becomes 10. I equals 5, 15. I equals 6, 21. I equals 7, 28. When I equals 8, my sum becomes 28 plus 8, 36. On the final iteration, I equals 9. My sum equals 36 plus 9, 45. The loop ran 10 times. I took values 0 through 9, and the accumulator collected the running total. The program prints 45. A quick shorthand. Instead of writing my sum equals my sum plus I, write my sum plus equals I. The plus equals operator takes the current value of my sum, adds I, and stores the result back. This notation exists because variable names can get long, and retyping them is tedious. Now suppose we want to sum from a start value to an end value, inclusive. We start set to 3 and end set to 5. The correct answer is 3 plus 4 plus 5, which equals 12. Here's a first attempt. We loop. For I in range from start to end. Inside the loop, my sum increases by I. We run it and the output is 7. That's wrong. We expected 12. This is the classic off-by-1 error. Range from start to end generates values starting at 3 but stops before reaching 5. It only produces 3 and 4. 3 plus 4 is 7. 5 never gets added. When output doesn't match expectations, insert print statements to inspect what's happening. We add a print inside the loop that displays the value of I on each iteration. Running the code, the console shows I equals 3, then I equals 4. That's it. Only 2 iterations. 5 never appears. This confirms the problem. Range with 2 arguments goes up to but does not include the stop value. The print statement exposed exactly which values the loop variable took. This is one of the simplest and the most effective debugging techniques. When your code gives unexpected results, print the variables you're unsure about. The fix is straightforward. Change the stop value from end to end plus 1. Now range generates 3, 4, and 5. My sum accumulates 3 plus 4 plus 5, giving 12, the correct inclusive sum. Whenever you need an inclusive upper bound in range, add 1 to the stop value. Range's stop is always exclusive. Commit that rule to memory. Let's apply the accumulator pattern to multiplication, computing a factorial. The while loop approach requires separate bookkeeping. Initialize a counter I to 1, set factorial to 1, test whether I is less than or equal to x, multiply factorial by I inside the loop, increment I and the loop back to the test. That's a lot of moving parts. A for loop collapses all of it. We set x to 4 and the factorial to 1. Then, for I in range from 1 to x plus 1. Inside the loop, factorial equals factorial times I. We use x plus 1 as the stop because range stops before its second argument. Range from 1 to 5 generates 1, 2, 3, 4, exactly 1 through x. The accumulator in action, factorial starts at 1. Multiply by 1, still 1. Multiply by 2, 2. Multiply by 3, 6. Multiply by 4, 24. 4 factorial is 24. The for loop handled initialization, incrementing, and the stopping condition all in one line. For loops and while loops each serve different purposes. Use a for loop when you know how many iterations you need, summing a range, computing a factorial, processing a fixed sequence. Use a while loop when the number of repetitions depends on a condition you can't predict in advance. Tools like Python Tutor let you step through code to build a clear mental model of how loops assign variables behind the scenes. 3 takeaways for loops: accumulate sums and products using the plus equals pattern. Print statements reveal what your loop variables hold, essential for catching off by one errors. And for loops, collapse initialization, testing, and incrementing into one concise line. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.